Okay, 1.3 is a pretty quick one. We're just estimating limit values from graphs, and I just want to remind you on our definition of limit and one-sided limit. So for a limit to exist, first of all, we need, oops, that's not the one I meant to choose. We need the limit as x approaches a from the left of the function to equal the limit as x approaches a from the right of the function. And then we say that the overall limit does exist, so whoops, no superscript on our notation there. And whatever it is, we can call it just L, right? So today we're going to work on just estimating this from graphs. And it's pretty intuitive as long as you remember a couple things. One, remember a limit is only concerned with what's the behavior of the function as we approach the limiting value. I don't care what's going on at the limiting value. We just are concerned with the behavior and the patterns as we approach that limiting value. So let's start with A here. They're asking us for the limit of g of x as x approaches 2 from the left. So I'm just going to trace along this. So this is our function g of x. Looks like a piecewise function. It's drawn in a couple pieces. So here's 2. So as I approach 2 from the left, what do my y values look to be approaching? Well, I would estimate that to be 3. So we're going to say the limit of g of x as x approaches 2 from the left is 3. Okay, so then B asks, all right, well, what about from the right? So now as we approach 2 from the right, so here's 2 again. I'm going to come in from the right. What do my y values seem to approach? Well, they look to be approaching 1. So I would say the limit of g of x as x approaches 2 from the right is 1. And again, I don't care what's going on at my limiting value of 2. I care about the behavior of the y values of the function as we approach, meaning as we get infinitely close from either direction that they're indicating. So lastly, what's the limit of g of x as x approaches 2 overall? Well, since a and b are not the same thing, the limit from the left of 2 is not the same as the limit from the right of 2. We would say that the limit of g of x as x approaches 2 does not exist. The limit does not exist. That's fun. That's a Mean Girls reference. All right. So now let's look at our limiting value is 5, and we're first approaching 5 from the left. So 5 is here. And as I approach 5 from the left, I'm getting infinitely close. My y values look to be getting closer and closer to 2. I'm going to call that 2. Okay, so what about from the right? So as I come in from the right, my y values are still getting closer and closer to 2. I'm going to call that 2 as well. Now, I don't care that there's a hole here, and it's actually defined such that f of 5 equals 1 here. That doesn't matter because when I'm just looking at limits, I don't care what's going on at the limiting value. I care what's going on as we approach the limiting value. And in this case, as we approach 5 from the left, our g of x values approach 2, and as we approach 5 from the right, our g of x values approach 2. So in that case, overall, we can say that the limit as the limit of g of x as x approaches 5 is 2. All right. All right, so our second example, we're not given a graph. We're actually going to graph this in our calculator, but it's the limit of sine x over x as x approaches 0. And one thing that we'll find out soon is that if you can do a direct substitution into your function and it actually does evaluate to something, then the limit exists and will be that. And so when I say direct substitution, I mean plug 0 in for x to both of these. The problem with this is that sine 0 over 0 is undefined. You cannot divide by 0, but that does not necessarily mean that the limit does not exist, and that's because this is actually what's called an indeterminate form. Sine 0 is 0, so we end up with 0 over 0. So this indeterminate form basically means that you can draw no conclusions right now. You have to figure out some other way to see if that limit exists. And so what we can do is look at our graphing calculator. All right, so let's go to y equals. All right, apologies. So we're going to go to y equals, and in this menu, we're going to plug in our function. So sine x over x. Oh, I'm going to go to mode and just make sure I'm in radian, which I am. And then I'm going to do zoom 6. Cool. Well, the limit that we're looking for, right, is just right in here as x approaches 0. And it does look like the y values are doing the same thing from the left and the right. And so I just want to get a little bit of a better window. So I'm going to go to zoom. Oh, no. I'm going to go to window. And I just really care about seeing what's going on near 0. So I'm just going to change my x min and x max to -1 to 1. And what we do know about the sine function is it never gets bigger than 1 or lower than -1. So I'll just change this to like minimum -1.1, max. Well, go to -1.1, max 1.1. And we'll just take a look, and right here, as x is approaching 0, it does seem to be approaching 1 from either side. So one thing we can do is go to our table and just use our table to do this. At 0, I'm getting an error, but remember what I really care about is what's going on as we get closer and closer to 0. So I need to, set up my table. Ask, okay. So let's get close to 0. 0.1, 0.01, 0.001, 0.0001. And let's get close to 0 from the negative side, right? So -0.1, -0.001, 0.0001. And your calculator here is just rounding it off to 1, but really it's taking it out to way closer. So it does seem that my y values approach 1 from either side. So I'm just going to use an educated guess on this one, and we're going to say, okay, the limit of sine x over x as x approaches 0 does seem to be 1 from either side. So we will get to a point this year where we can actually prove that using something a little bit more complex called L'Hopital's rule.
Yeah.
All right, let's try another one. So example 3, in the figure, we're shown a function f. It's a piecewise function, and we're just asked, which of the following statements are true? And so the first statement, the limit of f of x as x approaches 2 from the left is equal to f of 2. So if we approach 2 from the left, then we're going to be on this piece of the function. Here's 2. So as I approach 2 from the left, if I'm looking at what my y values are doing, they seem to approach -1. And what would f of 2 be? Well, f of 2 is wherever that point is filled in. So f of 2 is not this one, but it is this one, which is also -1. So both of these are -1, so I'm going to say the first one is true. All right, the second one, the limit of f of x as x approaches 6 from the left and from the right. Okay, so as we look at what's going on as we approach 6 from the left, remember, we don't care that what's going on at 6, at our limiting value. We just want to know the behavior as we approach 6. And as we get closer and closer, our y values, again, seem to get closer to -1. As we approach from the right, same deal. They approach -1. So those are equal. I'm going to say that's true. Now what about the overall limit of f of x as x approaches 6? Is that equal to f of 6? Well, that, in this case, we just found out that the limit is -1, but f of 6 is defined where that point at 6 is filled in. So it's at that case that we do care what's going on at 6. And at 6, f of 6 is clearly defined as -3. So these are not equal. This one is false. All right, so here's a little student example for you to try. Kind of similar to what we've been doing. So just go ahead and give me for each of these subsections, see if you can find the one-sided limit and or two-sided limit if it calls for it, and come up with a value. Practice writing out the full limit notation for each one. Don't just put the value or undefined. You need to get in good habits of using limit notation and one-sided limit notation. So try these 6 little sub-problems based on this graph, and we'll go over it in class.